Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 28, 2025, just yesterday. The standout result is a general-purpose humanoid that plays real table tennis with sub-second reactions, sustaining rallies of up to 106 consecutive shots against a human opponent. The paper is titled, HITTER, a humanoid table tennis robot via hierarchical planning and learning. And as we will see later, the approach delivers agile, human-like strikes. In short, a model-based planner predicts the ball and sets racket targets, while a learning-based whole-body controller executes coordinated, natural motions for fast, reliable returns. On X, reactions highlight the 106-shot rally, sub-second reaction times, and fully autonomous play, with praise for model-based planning plus reinforcement learning. Engagement appears solid, including a post with 362 likes. The previous figure set the headline claims, and Figure 1 makes them concrete with real match play. The left panel shows two humanoids rallying, which illustrates fully autonomous exchanges, where perception, planning, and whole-body control operate end-to-end. The right panel shows a humanoid returning shots from a human player, so the setup demonstrates sub-second reactions in mixed play. The multiple ghosted ball positions emphasize high-speed trajectories that the system predicts accurately. So the previous figure highlighted real rallies, and Figure 2 shows the full system pipeline that makes those exchanges possible. The top right panel illustrates motion capture feeding ball position and a desired landing point into a model-based planner, which outputs racket targets and strike time so the robot knows where and when to hit. The bottom band depicts the learning-based whole-body controller, trained with human reference swings that converts observations and planner commands into coordinated joint actions. The left panel anchors the hardware setup, including the racket mount and detectable ball. Alright, the previous figure laid out the pipeline, and Figure 3 quantifies how prediction improves as the strike approaches. The top plot shows target position error shrinking from about 8 centimeters to near zero, with the mean dropping below the red critical threshold around half a second before contact. The shaded band conveys variability, which tightens notably toward impact. The bottom plot tracks timing error, falling from roughly 40 to under 10 milliseconds by minus 0.1 seconds, so the planner gives reliable strike timing in the final approach. So the previous figure quantified prediction accuracy, and Table 1 details what information the policy and the critic received during training. The policy consumed proprioception and planner outputs, like target racket position, target racket velocity, base target, and time to strike, which kept control reactive. The critic included privileged signals such as full body poses, base linear velocity, time left, and human reference joints, so learning stabilized and imitation stayed natural. This split explains why deployment stayed zero shot while keeping motions human-like. Okay, the previous figure summarized training signals, and Figure 7 presents return performance on a virtual hit plane. The grid marks 20 centimeter squares, and colored dots indicate outcomes: blue for forehand returns, green for backhand returns, orange for hits that did not land in, and red for a miss. The distribution shows coverage across the plane with dense green on the right and multiple blue on the left, which reflects handedness and reachable zones. The caption states 24 successful returns out of 26 hits, so hit rate reached 96.2% and return rate reached 92.3%. Wrapping up, two takeaways stand out. The split between fast model-based prediction and a learned whole-body controller delivers sub-second, human-like strikes, and the approach transfers zero shot to real hardware with long rallies and high return rates. The implications reach beyond ping-pong to any rapid human-robot interaction. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.